All right, so today we're going to be learning about Lewis structures. You probably remember doing Lewis structures last year in chemistry, and most of what we're doing with Lewis structures is the same, but there are some additional things that we're learning this year that we did not cover last year. So Lewis structures are typically only used for covalent compounds. We don't usually use them for ionic compounds because as we discussed previously, ionic compounds are in these crystal structures with these repeating patterns, and they're best represented using those unit cells, crystal structures, rather than a Lewis structure, which shows a single molecule. The Lewis structure shows us how the valence electrons are arranged in the molecule, whether they are bonds or lone pairs. But they only show the valence electrons. So when we're dealing with a Lewis structure, we only want to include those valence electrons. We do not want to include all of the electrons, like the core electrons, because those don't really participate in bonding. So here's just a review of the rules for drawing a Lewis structure. The first step is to count all of the valence electrons. One thing you'll see this year that we didn't really do last year is charges. Some molecules have a charge, so you do need to pay attention to the charge. If it's a negative charge, then you're going to add electrons to your total. If it's a positive charge, then you're going to take electrons away from your total. Next, you want to determine which atom will be the central atom. Typically, it's the atom that there's only one of. There are some atoms that can never be central, like hydrogen can never be a central atom, fluorine can never be a central atom. There's some atoms that are usually central as well, like carbon almost always wants to be the central atom if it's in that molecule. Next, you want to draw a skeletal structure, so place that central atom in the middle and draw the remaining atoms around it. Then you connect the central atom to the outer atoms using single bonds. Remember, each single bond counts as 2 electrons. So you want to add up how many electrons you used and subtract that from your total that you counted in step 1. Next, you want to complete the octets of the outer atoms. So you give those lone pairs of electrons to complete their octets. Make sure you remember to count the fact that they have a bond. And then you want to subtract the electrons used again from the total in step 1. Finally, you want to put those remaining electrons, if there are any, on the central atom in pairs. They all have to be paired up on the outer atoms or on the central atom. The one time you use double or triple bonds is if there is not enough electrons for everything to have a full octet. So double and triple bonds are kind of a last resort. You want to wait to use those until you've checked if everything can have a full octet using only single bonds and lone pairs. The first molecule we're going to draw a Lewis structure for is CF4. So the first step is to count up the valence electrons. Remember, we do that by finding the element on the periodic table and counting the number of columns across that it is. So carbon is 1, 2, 3, 4, and fluorine is 1, 2, 3, 4, 5, 6, 7. So for carbon, we have 4 valence electrons, and there's only 1 carbon. For fluorine, we have 7 valence electrons, and there are 4 of them. So 7 times 4 is 28. And we add those up to get 32 electrons total. Next, we want to choose the central atom. So carbon will be our central atom here because there's only 1 of it, while there's 4 fluorines. And then we draw our fluorines around it. Next, we connect those with single bonds. Each single bond counts as 2 electrons. So we take our total, and we're going to subtract 2, 4, 6, 8. We're going to wind up with 24 electrons left. So the next step is to add electrons to the outer atoms until they reach a full octet. So each of these outer atoms has 2 from the bond. So to reach 8, they each need 6 more. So we added 6 to each of these fluorines. 6 times 4 is 24. So we have no electrons left over. Each fluorine has a full octet because we just gave it 8 electrons. And when we look at carbon, it actually has a full octet too because it has 2, 4, 6, 8 from the bonds. The next molecule we want to look at is N2. So again, we count up the valence electrons. Nitrogen has 5, and there's 2 of them, so we have 10 electrons total. Since there's only 2 atoms here, there's no central atom. We just put them next to each other and draw a single bond between them and subtract that from our total. We have 8 left, so we want to start by putting valence electrons around the outer atoms. Well, since there's no central atom, we can just try and put them as many at each one as we can. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, I used all my electrons. This nitrogen has a full octet, but this one does not. So what I need to do here, since I've come to the end of my electrons and I don't have enough to make full octets for everything, I need to share some of these extra electrons on this side as bonds so that both of them will have 8. So I'm going to take away some electrons here and make another bond. So now this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen has 2, 4, 5, 6. So we're closer, but we're still not at a full octet. So to fix that, again, I'm going to take electrons from this one that has more and make a triple bond now. So there's 6 electrons being shared, and each nitrogen has 2 in its lone pair, so those both have 8. The next molecule we're going to look at is NO+. So this one has a charge, so we need to consider that when we're counting up our valence electrons. So for nitrogen, we have 5, and there's only 1. For oxygen, we have 6, and there's only 1. So total, we would have 11, but we have a positive charge, which means 1 electron has been taken away. So we're going to subtract 1 from this total and wind up with 10. So just like in the last one, there's no central atom because there's only 2 atoms. So we just put them next to each other and draw a single bond between them. And then we go ahead and try and fill in our electrons. And you'll notice kind of a pattern here where we see that we don't have enough to fill up our valence electrons for oxygen. So we need to share them again, just like we did last time. And we're going to wind up with this triple bond and the lone pair on each. However, at the end here, this one is positive. So whenever you have a charged molecule, you need to draw brackets around it and then put the charge on the outside to show that that whole structure has a positive charge. So we do have quite a few exceptions to the octet rule. Remember, the octet rule is that every atom wants to have 8 valence electrons. There are a few atoms that want to have fewer. So hydrogen, for example, only has 2 electrons when it's bonded, and that's because it only has 1 proton to begin with. There's no way it can hold on to 8 valence electrons. Boron is another exception. Typically, it has only 6 electrons in a Lewis structure. So we call that electron deficient, but it is generally highly reactive. So you may see it with extra electrons. However, to draw the Lewis structure, you usually want to make it only have 6 electrons. There are a lot of elements that can actually exceed the octet rule. So once we get to the 3rd row of the periodic table, the elements start to have an empty d orbital. So in the 3rd row, they have an empty 3d orbital. In the 4th row, they have an empty 4d orbital, and so on. So those nonmetals in those larger orbitals can actually hold extra electrons because of that empty d orbital. So some of the common ones you'll see are sulfur, phosphorus, xenon, chlorine's another one you'll see, iodine, that can actually have more than 8 electrons. Okay, so we're going to take a look at some molecules that have atoms that are exceptions to the octet rule. So first up is HF, hydrofluoric acid. So as usual, we start out by counting up our valence electrons. Hydrogen only has one, and there's one hydrogen in the molecule. Fluorine has 7 valence electrons, and there's one in the molecule. So total, we have 8 valence electrons. Since there's only 2 atoms, there's no real central atom. We just draw them next to each other, and we can draw a single bond between them. That gives us 6 electrons left. Normally, we would try and distribute those equally among hydrogen and fluorine. However, hydrogen is one of our exceptions, and it only needs 2 electrons to be satisfied. And so what we can see here is that it already has 2 from this single bond. So since it has 2 electrons already, we don't need to add any lone pairs to it. In fact, adding lone pairs to hydrogen right now would make it less stable. So hydrogen is done. So instead, we take these 6 electrons and we add them to the fluorine. And now we can see that fluorine has 2, 4, 6, 8 electrons. So it has its full octet. Hydrogen does not, but it has 2, which is what it wants. So this would be our correct Lewis structure for HF. The next example is BH3. So boron has 3 valence electrons, and there's 1 in the formula. Hydrogen has 1 valence electrons, and there are 3 of them in this molecule. So total, we have 6 electrons to use. We need to choose a central atom. It's most likely going to be boron here because it's the only one of its type. And we draw those hydrogens around it. And then we can add single bonds to connect them. So we used 2, 4, 6 electrons, giving us 0 left. So let's look. Hydrogen only wants 2 electrons in the end, and each hydrogen has a bond which represents 2 electrons. So the hydrogens are good. They don't need any more lone pairs or valence electrons. Similarly, boron only wants 6. Most atoms want 8. Boron's one of our exceptions. It only wants 6. So let's check. It has 2, 4, 6 from its bonds. So it is also good. And so this is our Lewis structure. Even though nothing has 8 electrons, this is the most stable way to draw this. Another example here of exceptions to the octet rule is SF6. So let's look at this one. Sulfur has 6 electrons, and there's 1 of them. Fluorine has 7 electrons, and there are 6 fluorines in the structure, so that's 42. So total, we have 48 electrons to go around. We're going to put sulfur in the middle because it's the only one of its kind, and then we're going to put fluorines around it and add single bonds. So we added these single bonds, 2, 4, 6, 8, 10, 12. We're going to subtract that from here. We have 36 electrons left. So the next step after bonding them together is to give those outer elements 8 valence electrons. So they'll each need 6 more because they have 2 already from the bonds. And 6 times 6 is 36, so we used up all of our electrons. So now we know fluorine is good because we just made it have 8. Then we look at sulfur. Sulfur has all these bonds around it, so it has 2, 4, 6, 8, 10, 12 electrons, which normally for a lot of atoms is not okay. But for sulfur, this is actually fine because sulfur has that empty d orbital that allows it to expand its octet. Resonance occurs when you have a molecule where you can draw more than one valid Lewis structure. Typically, this happens when you have double or triple bonds in the structure. And so you wind up with multiple structures that can be drawn. When you come across something like this, you do need to draw all of the resonance structures, all of the possible structures, because the actual molecule is not just one of those structures, it's actually an average of all of them. So for example, NO3 minus is a molecule that has some resonance structures. And in the structure, when you draw one of them, it has one double bond and two single bonds. But in real life, it actually has three equivalent bonds. Those electrons are we call them delocalized. They're able to move from one bond to another. And we'll talk a little bit more about that in some subsequent lessons. But resonance structures allow us to kind of show this gap in the Lewis structure model. Because Lewis structures, since we're drawing them on paper, they can only have single, double, or triple bonds. But these bonds in resonance structures are actually different from a single, double, or triple bond, because those electrons that are participating in the double bond are delocalized. They can move from one bond to another. And it's hard for us to show that in one structure on paper. And so we need to show all of the different Lewis structures in order to show that those electrons could be in any of those possible locations. A lot of molecules have resonance, which means that there's more than one valid Lewis structure that we can draw. So let's take a look at a few examples of those. O3. So oxygen has 6 valence electrons, and there's 3 of them in the molecule. So we have a total of 18 electrons to use. Since they're all oxygen, it doesn't really matter which one goes in the middle. And we start out the same way as usual by connecting them with single bonds. So we used 4. We have 14 left. So as normal, we're going to try and fill up the octets of the outer elements first. So 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We used 12 to get those ones stable. So now we have 2 left, and those remaining electrons go on the central atom as a lone pair. So each of the outer atoms has that full octet, but the middle atom, we can see, only has 2, 4, 6 electrons. And so when we have a structure where they can't all have 8 and they need 8, we have to share them again to make a double or a triple bond. So I'm going to take some electrons from this side and make a double bond. But that's not the only way I could have done this, right? If I redraw what we just had, instead of taking the electrons from the oxygen on the left, I could have also taken those electrons from the oxygen on the right. These two structures are equally valid. They both have the same stability. And so these are resonance structures. To show that they're equal, to show that they're resonance, we draw this arrow between the two of them to show that both of these structures are taking place. These electrons that form this double bond can be in either of those locations. So this is new. Formal charge is something we didn't really talk about much last year. So in some cases, when you're drawing the Lewis structure, you'll be able to draw it in multiple different ways. And this could be resonance, or it could just be different ways of putting the atoms like in order, different central atoms, things like that. Formal charges are used to identify the most stable structure, and the most stable structure is the most likely one to happen. If we have formal charges on our molecule, we want them to be as close to 0 as possible. So the ones the structure with the lowest formal charges is going to be the most stable or the most likely structure. When we have a neutral molecule, like no charge on the molecule, all of those formal charges on each atom has to add up to 0. So even if all the charges are not 0, if we have like some positive or negatives, they have to add up to 0. If they don't add up to 0, it means we're doing something wrong. If we do have a charge on our molecule, like a +1 or +2 or negative, then our formal charges need to add up to whatever that charge is. To find the formal charge, we take the difference between the number of valence electrons that the atom starts with and the number of electrons that it has in the molecule, so from the bonds and lone pairs. So the lone pairs belong only to the atom that they're drawn on, but the bonds are shared equally. We just assume they're shared equally when we calculate formal charge. We're not looking at like electronegativity differences or anything. So for each bond, each atom in the bond gets 1 electron. So again, we try to get formal charges that are as close to 0 as possible. That will show us which structure is the most likely to occur. So to calculate the formal charge, you first figure out how many valence electrons are on the atom. And remember, we do that from the periodic table. Then we're going to subtract how many lone pair electrons there are. So how many dots basically are around that atom. And 1/2 of the shared electrons. So how many bonds basically does that atom have? Then we make sure that the formal charges add up to the charge on the molecule, whether it's 0 or otherwise. We have to check to make sure that those add up. And then to choose the most stable Lewis structure, we want to find the one that has the formal charges that are closest to 0. Another thing to consider, if they're not 0, the more electronegative elements will want a more negative charge, and the less electronegative elements would be happy with a more positive charge. So, if you have two structures where in one of them, oxygen has a positive charge and in the other, oxygen has a negative charge, well, oxygen is pretty electronegative, so it's going to be more stable with the negative charge than it will be with the positive charge. So if they don't have zeros for their formal charges, and you need to compare them, the more electronegative the atom is, the more it will want a negative formal charge. All right, so in this example, we're trying to find the most stable Lewis structure of XeO3 based on the formal charges. So first thing, we start out like normal. We have to count up the valence electrons. Xenon has 8, and there's 1 of it. Oxygen has 6, and there's 3. So 8 plus 18 is 26. So we start by drawing our skeletal structure. Add in those single bonds. And then we can fill in the octets of these oxygens. And the remaining 2 electrons can go on xenon. Now this one's complete, but we can draw other structures for this as well, because xenon is one of the exceptions that can have more than 8 electrons, and it's actually more stable with more than 8 electrons. So in order to give it more than 8, we're going to start giving it double bonds. So I'm going to take electrons from one of my oxygens, and make a double bond. But as we saw with resonance, if I do that with this one, and I could have done it with these other ones, I have to draw those as well. But xenon still can have more, so we're going to actually add another double bond to it. And again, because we did that here, we have to show any possible combinations of that. And finally, we can actually add one more double bond so that they're all double bonds. All right, so how do we know which one is the best? In order to figure that out, we need to go through and check our formal charges on each element. Remember that we want formal charges that are as close to 0 as possible. So starting at this first one, we take the number of valence electrons that the atom had originally, and we subtract, basically we subtract 1 for each dot and 1 for each line. So oxygen has 6 on the periodic table, so we can go 6, 5, 4, 3, 2, 1, 0, -1. Each of these is in the same situation, so they're all going to be -1. Xenon starts with 8, so 8, 7, 6, 5, 4, 3, so that's going to be +3. So let's see if we can get closer to 0. So in this case, these oxygens are the same as before, so I'm going to keep them at -1, but this oxygen is different, so 6, 5, 4, 3, 2, 1, 0. Okay, so that's good. And then xenon has 8, 7, 6, 5, 4, 3, 2, +2. These will all be the same, just arranged differently. So then here we've got a new situation, so 6, 5, 4, 3, 2, 1, 0, -1. 6, 5, 4, 3, 2, 1, 0. This one will be the same. 8, 7, 6, 5, 4, 3, 2, 1. So we're getting closer. We're getting less and less charges. All right, so in this one we have 6, 5, 4, 3, 2, 1, 0. All of our oxygens will be the same. And xenon has 8, 7, 6, 5, 4, 3, 2, 1, 0. So the one that has the most formal charges closest to 0 is this one. So that will be our most stable Lewis structure.